Mathematical operations give us the power to manipulate numbers in a variety of ways. For example, consider some common operations in combination with the number 2. We can add 2, which shifts numbers up on the number line. We can also subtract 2, which shifts numbers down on the number line. We can multiply by 2, which stretches numbers away from 0. And finally, we can divide by 2, which compresses numbers towards 0. Together, these 4 operations that we just performed make up the basic arithmetic operations, and when we combine these operations with a variable, we get a linear expression. These are all examples of linear expressions. Notice that all of these expressions contain variables that have been combined with numbers using the 4 basic arithmetic operations. But what truly makes an expression a linear expression? Well, one answer is that a linear expression is a polynomial with a degree of 1. But that explanation might raise more questions than it answers, so let's try to build a more intuitive definition for now. One way to better understand a category is to look at items that don't belong in that category. So let's look at some examples of nonlinear expressions alongside our linear expressions. In this first example, notice that the x is squared. Anytime our variable is raised to a power other than 0 or 1, the expression is nonlinear. Our next example looks a bit deceiving because the only operations that are occurring are division and subtraction, which are both basic arithmetic operations. However, notice that we're dividing by x, which is not allowed in a linear expression. We are allowed to divide x by a number, but not the other way around. Then, here are a couple more examples of nonlinear expressions. Notice the variable under the square root and the variable in the exponent, which are both not allowed in a linear expression. And finally, this last example might look linear at first, but when the expression is simplified, it has a y squared in it, which is nonlinear. Its counterpart in the column of linear expressions, however, simplifies to a basic linear expression. In the end, all single-variable linear expressions can be written in the form mx plus b, where m and b are numbers. Nonlinear expressions, however, can never be written in this form. With that, it's time to evaluate some linear expressions. Let's start by taking another look at 2 of the expressions that we had on the previous screen. Each of these expressions contains the variable x, so if we choose a value for x, we can then find the value of each expression. To start off, let's let x be equal to 16. When we substitute this value into the first expression, we get 4 times 16 plus 3. 4 times 16 is 64, and when we add 3, we get 67, so our first expression is equal to 67. Our second expression can be similarly calculated by dividing 16 by 8 to get 2, and then subtracting 7 to get -5. Now, let's have x be a negative number. The first expression is pretty straightforward, but in the second expression, we end up getting a fraction after dividing by 8. This means that we need to convert the 7 into 56 over 8 so that we have a common denominator for both fractions. Then we have -3/8 minus 56/8, which is -59 over 8. Finally, let's have x be a fraction. In our first expression, we can rewrite the 4 as 4 over 1 so that we can see how to multiply the first 2 numbers more clearly. Then, we need to convert the 3 into 15 over 5 so that we have a common denominator for adding. This gives us an answer of 63 over 5. Then, in our second expression, notice that dividing by 8 is the same as multiplying by 1/8. This gives us a product of 12 over 40, which reduces to 3/10. After we subtract 7, we end up with a final answer of negative 67 over 10. On this screen, we used a table to indicate the relationship between the value of x and the corresponding value of each expression. And we'll come back to that idea later. But in our next two sections, we'll explore function notation as an alternative way of expressing this relationship between variables and expressions. Before we get into formal function notation, though, let's explore a more visual way of representing functions: the function machine. The purpose of a function machine is to emphasize a key property of functions, that for each input value, there is a single output value that corresponds with that input. And in general, this output value will be reached through a sequence of steps applied to the input. With these concepts in mind, let's draw some function machines. We're going to model our function machines after a tube or a pipe where the input, or starting value, is placed into the top of the pipe. The input will then move through the pipe and encounter operations along the way before leaving the bottom of the pipe as an output. Now that we have a couple function machines drawn, let's take a look at the process of plugging numbers into our function machines. Let's start by plugging 16 into both of our machines. In our first machine, the first step that the 16 encounters in its path down the pipe is to multiply by 4. This results in a 64, which continues to move along the pipe until it encounters an instruction to add 3. This results in a 67, which comes out the bottom of the pipe as the output. Plugging 16 into the second machine follows a similar process, resulting in an output of -5. While this may be a visually interesting way to show the input-output process, we can make things much simpler by giving our functions names. While these names could be anything we want, the normal protocol is to use letters, often f and g. So let's call our first function f and our second function g. Then we can write equations like these to indicate the relationship between input and output. Notice that the input value goes in parentheses immediately after the name of the function. Often, parentheses like this are used to indicate multiplication. But now that letters can be used as function names in addition to their use as variables, this instead indicates that the number in parentheses is being placed into a function. This expression is then said to be equal to the output of the function for the given input, and we read these equations as f of 16 equals 67 and g of 16 equals -5. Once we have this notation in place, you might notice how easily we are able to represent input-output pairs. For example, if we input -3 into f and g, we would get the outputs of -9 and -59 over 8, respectively. We can easily represent this by saying that f of -3 equals -9 and that g of -3 equals -59 over 8. The same goes for if we have an input of 12 over 5. Now here's the thing about function machines. While we'll continue to use them from time to time to help us gain a better understanding of how functions work, they aren't the most convenient way to represent the steps of a function. But how should we come up with a more convenient notation? Well, it turns out that we already have the pieces in place. All we have to do is plug a variable into our machine. Let's do this by plugging x into f. When we put x into the f machine, the first thing that happens to it is multiplication by 4. Now, while we could write this as x times 4, we can also write this as 4 times x, or simply 4x. The next step that happens inside the machine is addition by 3. And when we add 3 to 4x, we get the expression 4x plus 3. This means that f of x is equal to 4x plus 3, which is a concise way of representing the steps of the function without losing any information about those steps. In a similar fashion, we can plug x into g to determine that g of x is equal to x over 8 minus 7. This function notation is often called a function rule and is the most common way to represent the steps of a function. Now that we've learned the basics of function notation, let's do some more practice with functions to solidify the process in our minds. To do this, let's take a look at these two functions and start by calculating f of 21. Notice that when we write f of 21, we are simply replacing the x in the original function notation with a 21. So when we write the other side of the equation, we can also replace any x's that we see on that side with the number 21. This gives us the expression 2 times 21 over 7 plus 11, which evaluates to 17. Thus, f of 21 is equal to 17. We can evaluate g of 8 in a similar fashion. Notice, however, that in our representation of g, the letter x occurs twice. This means that when we substitute 8 for x, we need to replace both x's with the number 8. This gives us the following expression, which ends up evaluating to negative 47. So g of 8 is equal to negative 47. And before we move on to another type of problem, here are a couple more examples of evaluating functions at specific values. One special item to note is that when we are substituting in values for x, it's a good practice to put those values in parentheses. As we evaluate more complicated functions and use more complicated expressions as our inputs, this practice will help us avoid certain common errors. Now that we've seen several examples of evaluating functions at specific values, let's try one final example of function notation. Suppose the input of our function is another linear expression, like 3t minus 14. When we replace x with 3t minus 14, we get this expression. And while we could leave our answer like that, it's common to simplify the resulting expression to achieve a less cumbersome answer. While function notation is a convenient way to represent inputs and outputs, there is another common method that we want to be familiar with as we move through this video series: tables of values. So to start things off, suppose we have this function and want to know what the outputs will be when the inputs are 0, 1, and 2. To figure this out, we just have to plug these inputs into our function and calculate the result. We can even summarize our results this way to easily see them in one place. This does look a bit clunky though, especially since we're writing the letter F so much. To avoid this and keep the focus on the numbers, we can instead make a table of values. To do this, we start by drawing a cross shape, often called a T-chart, and we label the columns as x and f of x. Next, we list out the input values that we want to plug in for x in the first column, and then we list the corresponding output values in the second column. This way, we can see from the column headers which numbers are the inputs and which are the outputs, but we don't have to write the letter F over and over again. And for a finishing touch, Let's add a couple more values to the table to see what happens when our inputs are negative. Let's conclude this video with one more example of a table. But this time, instead of just showing the input and the output of the function, we're going to use our table to show the steps we took along the way. So suppose we have this function. Now, we could distribute the 7 and simplify, but let's keep the function as it is for this example. In a typical table, we would simply have two columns, one for x and one for g of x. But what's the first thing happening to x? Well, we're subtracting 3. So while we're still going to have x in our first column, let's have the second column represent the value of the function after we subtract 3. We'll represent this by titling the column x minus 3. Then, the next step we're taking in the function is to multiply by 7. So let's make another column titled 7 times x minus 3. And finally, we add 5 to achieve the output of the function. Notice that we could simply call this column g of x, but let's stick with our current pattern and label it with 7 times x minus 3 plus 5. Now that we've established what each column is going to represent, let's pick some values for x and fill in our table. We'll go with the integers from -1 to 5 because those inputs should give us a good variety of outputs. Now, the nice thing about setting up our table this way is that we don't have to evaluate the whole function at once. Instead, we can simply go one step at a time. And that first step is to subtract 3 from our inputs. This shifts all of our values down by 3, but still results in a set of consecutive integers. Then, our next column is just 7 times the value in our second column, which results in a column filled with consecutive multiples of 7. And finally, we need to add 5 to our results from the third column to get our final outputs. This extended table of values might take a bit longer to make than a normal table, but it also has the potential to show us patterns in our data that we may not have seen before. That concludes this video on evaluating linear expressions. Hope you learned something new, and thanks for watching.